entrants and beyond. Welcome to day 10 of my DSA series. So today I will be discussing question number 144, binary tree pre-order traversal. Thus far I've mainly discussed questions related to arrays and sliding windows. So if you ever face difficulties in those questions, you can check out my videos thus far. And let's dive right into the question. So the question states, given the root of a binary tree, return the pre-order traversal of its node's value. So we basically have to return the pre-order traversal of a given tree, and we will be given its node. And over here it's given that we basically have a struct tree node. It has a value, it has a left, it has a right, a left pointer, right pointer, and then this basically shows the different ways in which it can be initialized. So let's look at the test cases. The first test case is 1, 2, 3. This is basically the tree that we have. So the pre-order traversal over here is 1, 2, 3. This is the second case. Over here the pre-order traversal is 1, 2, 4, 5, 6, 7, 3, 8, 9. 1, 2, 4, 5, 6, 7, 3, 8, 9. Over here the root or our tree is empty, so we can just return that. Over here our tree just has one element, so that would be the only element that will be part of the pre-order traversal. And here the constraints are given. The number of nodes in the tree is in the range 0 to 100. The value of node goes from -100 all the way up to 100. And the follow-up is given, recursive solution is trivial, could you do it iteratively? So I would recommend you to go through the theory about trees. If you're new to trees, you should definitely watch some videos regarding trees and maybe check out some articles on Geek for Geek or Medium or even on LeetCode discussion before you jump to this question, because things won't make sense to you if you don't know the basics about trees. And if you are familiar with trees, kind of know the basics, then I think you can continue watching this video. So let's dive right into the solution. So I'm going to basically show the iterative way to solve this question, because the recursive way, like it was mentioned, it's really trivial, so you can easily do that yourself. So I'm going to show the recursive way, or sorry, the iterative way to solve this question. How do we get the pre-order traversal of a given tree given in the recursive way? So what happens in a pre-order traversal is we basically return our root first, then we return the left, then we return the right. This is what happens in pre-order traversal. There's basically two types of traversals in trees and in general, DFS and BFS. So DFS is depth first search, where we go down into the depth up until we can't go deeper anymore, and we basically return the order according to that. And breadth first search, we go level by level. So over here, breadth first search is also known as level order search. So the breadth first search would be like 1, then we go to the next level, discover that, next level, discover that, next level, discover that. And just a thing to note, whenever we are dealing with DFS, by default we use a stack, and when we're dealing with BFS we use AQ. And that things like this would make a bit more sense. If you have some idea about graphs, I think you'd be able to grasp that, but it's fine. So I'll basically first show how the pre-order traversal works in this case, and then we can go on about understanding the approach and how we're going to solve it. So I basically mentioned this root, left, right, correct? So let's dive right in. So what would happen is we're going to start off over here. So first we print the root. So we add that, suppose this is output, we add 1. Then we go to its left. Now this is the root. We add 2. Now we go to its left. This can be treated as root. So we print 4. This doesn't have a left or right. Good to go. If we look at this tree, so what can we see? We can basically see that we've traversed the root. We traversed the left. Now we have to traverse the right. So we add 5. We go to 5 to the left then. Done. 6. This doesn't have anything, so we must, if we look at this subtree, we can understand that we must have 7 now. 7. Now if we look at this entire big tree, you can see the root is done, left is done, we must go to the right. Right node is 3. 3 doesn't have a left node, so we then directly add its right node. This has a left node of 9, so that comes into play and there's nothing left. And as you can see, we've been able to traverse the entire tree using the pre-order traversal technique. So hopefully this did make sense to you. If it doesn't, you can maybe watch this, rewind and watch the video again. Things would probably make sense. But the underlying philosophy is simple: root, left, or right. That is all that we have to do in order to solve these questions. That is pretty much all that we have to do. It's nothing that complex. So now let's show how to do it using a stack, or using the iterative way. So we all know that in recursion, in the backend, basically a stack is employed. So if we want to solve this using an iterative approach, we must basically mimic the behavior of a stack, right? If we don't mimic the behavior of a stack, we won't get the appropriate output. So one thing's clear, we need a stack. So suppose this is our stack. One thing's clear, this is our stack. And we are going to have an output place where we're basically going to store the output, whatever we get. And we're going to have another variable, let's call that variable t, basically denoting the top of the stack. Now there are two edge cases. You can clearly understand if there's just one node, in one node we can just return that. And how do you know if there's one node? We can just check if root's left is null and right is null and root is not null. That basically means there's only one node, so we can simply add that to our output vector and then we can return that. Simple as that. Voila, we're done. And if there's no nodes, like we saw in one case, we can directly return an empty vector. And how do we know there's no nodes? If root is null, we can say that there is no tree, or there's no nodes in the tree, so as to say. Now in this case we can see that none of these conditions meet. So first condition, is root null? Nope. Is roots left and right null? Nope. So that means we have a tree with ourselves. So what we're going to do is first we're going to add one directly into the stack. We're going to add one to the stack. Now when we did the pre-order traversal, something that you probably noticed is that we need to keep track of what one's neighbors are, because if you don't know what's one's left and we don't know what's one's right, we can't really do a pre-order traversal. So we must store that somewhere, correct? So how can we store that? So we can simply store it in the stack. But before storing it in the stack, what do we have to do? We can take a top variable that's going to store a stack.top. So over here, stack.top is basically node 1. So this is node 1. I'm not talking about value 1, it's node 1. Now after storing it, what I can do is I can pop it. Now you might be wondering, why are we popping? Like, shouldn't we just store everything and then do it something like in that sort of fashion? Now why do we pop? We basically have to store one somewhere, correct? Because we can say that we're at the root and we know it's root left, right, so we must return root. And if I add something extra onto the stack, one will never be on the top. So how in the world can I return one, or how in the world can I store one somewhere? And if I can't do that, it defeats the entire process. That's why what we're doing is we're storing one, we're putting it into the stack initially, we're making top equal to that node so that we know what its left is and what its right is. Once we've done this, we can simply pop, we can take top's value, put it in an output, and we know after we're traversed one, we have to look at its left and we have to look at its right. So my question to you is, do we need left first or right first? So you'll be, yeah, we need left first. Didn't you just say that it should be root left, right? Yep. So what should be the order in which I put it in the stack? You might be wondering, why does that matter? Why can't we just put left and right? That logically makes sense, right? Because that's what we're supposed to do. But you're wrong over here. If you go into the fundamentals of a stack, you know it's a last in, first out sort of data structure. So whatever value goes in last, that is the value that can be popped. So suppose you said, nah, it doesn't really matter, we just put 2 in here. Okay, so I'm like, fine, let's put 2 in there. And then we put 3 in there. Now how in the world can we pop 2? We cannot get 2, and we know we have to store 2 in the output. But we can't do that. And you might be wondering why that's happening. So it's because of LIFO, last in, first out. So we want the left value to be on the top. So how could we do that? We push the right value in first. That is all that we have to do. So that's simple. We're going to check if the left is not null. And first we're going to check if the right is not null. We can push that right in. Left is not null. We push that left in. Now top becomes 2. We can pop this 2. We add this 2. Now we are in this tree, so we must include the left. So again, same logic. This is the left, this is the right. What do you put in first? Right. So we put in right in, and then we put 4 in. Ready to go. We pop this 4, we store it somewhere. 4, we pop it, we add it. Now for 4, there's no left and right. That's why I mentioned we check for the condition. Is left not null? Is right not null? So both of them are null. Is anything gonna be pushed? No. But do we continue with the operation? Yes. Why? Because our stack is not empty. We take 5. 5 would be our top. We store it in our variable. What do you do after storing? You pop. What do you do after popping? You put it into the output. Now we are done. 5 has 2 nodes, left and right. What do you put in first? Right. So we put in the 7, and then we put in the left. We put in 6. Top becomes 6 now. Once top is 6, we can pop it. We can put it in over here. It's left, its right is no, first of all. Don't push anything. Left is no, don't push anything. Do we continue? Yes, we do. Stack is not empty yet. For 7, now top becomes 7. We store that in output. What do we store in output? We store 7 in our output. Clear? We store 7. No worries as such. We just take this 7, we store it. What are the neighbors of 7? There are no neighbors. Or what are the left and right nodes? There are nothing that is present below this. We're done. So essentially at this point of time, we already traversed the left part of this node. So once left, we already traversed it. But do we continue? Yes, we do. 3 is still left. What do? Top becomes 3. We store 3 right over here. We pop 3. What is the left of 3? What is the right of 3? We first push that. Left of 3, nothing. 8. Now our top becomes 8. Once our top becomes 8, what do? We pop it. We store it. And what is the right neighbor of 8? It's nothing. Nothing happens. 9 is the left neighbor. Yes, it is. This becomes 9. We can then pop our 9. 9 gets pushed. Now our stack is finally empty, and voila, we are done with the traversal. So hopefully that did make sense. I try to kind of make it exciting for you guys, because like when I was studying, I really got bored, and I saw a couple of videos. They actually did make sense. But if you go into the logic, I think DSA basically starts making sense to you, and just be consistent with it. So now let's write down the code. So what do we do in the code? Just think about it. Think in your mind what we did. What was the first thing that I mentioned? We want to replicate what happens in recursion. So when you recall recursion, what happens in recursion? We use a stack. So we are going to store a stack. Now what's going to be stored in the stack? Is it going to be node's value? No, we need to store the node itself, because as I mentioned, we need to know its left and right. And if we don't store the node, how in the world can we know its left and right? So it's going to be simple. Tree node star s, simple as that. We need a vector int output. How do you know that? The function says that, the question says that. That makes sense. Now I mentioned 2 edge cases. What were they? What if there is no node? So if root is equal to no, what can we say? If root is no, it's simple. We can just return. We can return an empty vector. The second case, what if there's one element? How can you say that? Now, since if is already checked, we can directly check if root of left is equal to no. There's nothing in the left of root. And root of right is equal to no. What do we return? We just return root's value. So return root's value. Done. This is done to handle the edge cases. Now we know we continue to basically do operations till our stack is not empty. So should I directly do while stack is not empty? Should I do this? Should I do while s is not empty? I can't do that, because that's going to turn out to be true if I haven't pushed anything. So what do you push in? Simple. In output you push what? Now vectors type is int, so we must push an int. How do we push in an int? We can just do root value. Simple as that. We take root, we push it in, and now we have our stack. Now like I mentioned, we need to store the top, so we need a tree node star, because our stack has this. T is equal to s dot top. They stored it. Now we can simply do s dot pop. Done. We have been able to successfully pop s. Now what did we do after popping? We stored its right and then left. And before doing that, we must check, does it even have a right and left? So we can say if t is right is not equal to no. What did we do? We just did stack dot push. What do you want to push? We want to push t is right. Done, sir. Now we do the same thing for left. We first check. Left shouldn't be no. It's not no. We can just do as dot push t of left. And did I forget something? Yep, I didn't add anything to the vector, so we can do it right over here. We can just do output dot push back. What do you have to push back? What do you have to push back? That's my question to you. We have to push back the value. So t is value. And now we can return output. This was our entire approach. Let's try to run it and see if it works. Let's try to run it and see if it works. It's taking its time. Okay, we messed up somewhere. Now, where did we mess up? Let's see. Okay, yep. We don't have to do this. We have to do stack top push. Stack top push. And what are we pushing in the stack? We directly push the root. Like I mentioned, it's not going to return anything because we didn't push the root. So basically our stack started off as something empty. And how can you do that? Now you can see it ran. So I was just trying to show a way to code. So like once you have the logic, you just have to think in detail. You have to understand what data structures we took, how to go in it, and then you can easily solve this question. Now I won't go into iterative. I won't go into the recursive approach. You can find that anywhere. But before actually doing that, you should probably look into the recursive approach. So I have the code. If you want to refer to it, I have the code. I had submitted it like yesterday. So I have the recursive code as well, just if you want to refer to it. So it's simple. I basically defined a function. So if root is null, we know we can return. So then we basically push in value. Then we call the function for root left, call the function for root right. That is all that we do. So that is the other approach, just in case if you want to use it. Now this is the code. Try to understand what's happening in the background with the stack. But now that I've shown you what's happening with the stack, this approach is really easy. It's really easy. You'll probably understand what's happening, so I won't go into the details of that. So yeah, thank you so much for tuning in. Hopefully this made some sense. Adios. See you tomorrow.